we present DLO-Splatting, tracking deformable linear objects using 3D Gaussian splatting. This work is a shared research effort between researchers from the University of Illinois, the KTH Royal Institute of Technology in Stockholm, and the NASA Ames Research Center. We contribute a method for estimating the 3D shape of a deformable linear object, short DLO, from multi-view RGBD images and gripper state information via a prediction update filtering approach. Tracking the 3D shape of a DLO is challenging due to self-intersections, as in the crossing of the blue rope, occluded states, for example when a gripper is in front of the camera, incomplete observations when the rope goes out of bound, and generally complex DLO dynamics. We start our method by initializing the DLO as a node chain from an existing method called trackDLO. From the initial state estimate, we use position-based dynamics to propagate the rope forward in time. To closer align the prediction with the actual image observations, we model the DLO appearance with a set of 3D Gaussian distributions, where each Gaussian models the local appearance of the rope at a certain point. The position of each Gaussian is represented relative to the DLO nodes, therefore connecting appearance and geometry. This means if the rope deforms, the Gaussians get deformed alongside it. Using 3D Gaussian splatting, this allows us to render an image of the rope state. Since this is fully differentiable, this allows for the formulation of an image-based rendering loss, which is then utilized for a gradient-based position update to update the rope state. While the method is still under development, initial experiments already show promising tracking results. In this challenging scenario, despite the severe occlusions from the gripper, the rope state is continued to be tracked. Anyhow, we observe clipping artifacts in the knot of the rope, and initial problems to reliably track the tip after it has been dropped from the gripper. Our baseline track DLO fails completely in this challenging scene. Current limitations of the model include the low fidelity dynamics model, general difficulties to prevent self-intersections during the image update, the slow update rate of 1 to 2 Hz. Anyhow, based on the promising experimental results, we conclude that DLO-Splatting shows promising tracking results in scenes with occlusions and challenging rope states. We thank you for your attention and are open for your questions.